Hi, everyone. Welcome. This is going to be such a rad lesson. So, yeah, I need the drums, but all right. So we're going to be on this for quite a bit. So 3 to 4 days, we'll see how we go. And this is going to be day one of that. And as you can see, we are going to be talking about radical functions. So you may wonder, well, how does that relate to what we did before in lesson one? Don't worry about it. You'll soon see. And so for the warm up right here, all you needed to do, oh, again, this is on page 19, volume 2. You're literally just solving for x. So see how it's already solved for y, and this is how we normally see it. But we're going to, change things up a bit and just solve for x. And literally, you're just going to just leave y as y, but you're going to, what is it called? We're going to treat it like a number is basically what we're going to do. And then just get rid of all the stuff on this side where x is, and then have x by itself is what we want. And if you have not done that already, pause, do a thing. All right, and here's the work for you. Just remember that when you, I would compare your answer with my answer, make sure that you got that same answer. Please make sure for the first one, you add 1 on both sides first before you square root. That's really key, because if you just square root it first, then you're kind of stuck. There's nowhere for you to go. So make sure you add 1 first, get the square root by it, or the square by itself, then you square root both sides. It's just like how we did here. And remember, when you square root both sides, you do have to include the plus or minus. All right. And reason being that, remember, like if we had, if you have x squared is equal to 9, right? If x squared is equal to 9, then 3 squared could equal 9, so x could equal 3. But x could also equal -3, right? Because if we look at -3 times -3, that also gives you a positive 9. So it could be both. So it could be 3 or -3, or the way we write it succinctly is plus or minus 3. All right, which means 3 and -3. So that's what we have to account for both answers. We got the positive side and also the negative side. Those are both feasible answers. Same thing with the second one. A note here that we're multiplying both sides by 4, because in order to get rid of this fraction, notice the numerator is just 1. So we don't really, that doesn't matter that much. But if this was, so since the denominator is 4, that's why we're multiplying both sides by 4. If, for example, our denominator or our numerator was, let's say in class, I used 3, I believe. So if I use 3, so if that was 3/4 that we're multiplying by, easy way to get rid of 3/4 is to multiply by 4/3, right? So then the 3's would cancel out. Oh, not those ones. The 3's would cancel out, and then the 4's would cancel out, right? Because the 3/3 is 1, and then 4/4 is 1, and 1 times 1 is 1. And all we have left is 1 times x squared, which is just x squared. So it leaves us with just the x squared, which is what we wanted to do, right? And that's what we mean by cancel out. All right, so let me take out the 3's because that's actually not part of the thing. And also another thing to note, the answer square root of 4y is not wrong. You just need to simplify it. So make sure that you use what's square root of 4? 2. So that's why it's no longer in the square root, because we've already used it up. You can't like keep on having it magically reappear, right? Some people will be like, oh, square root of 4y. Oh, that's like square root of 2y. Can't do that. That is magic, right? Magic doesn't happen in math. If it looks like magic, then you just don't understand why. But there's always a y involved in that. Okay, so that's what we have the 2 on the outside of the radical, because we've already used it. But for square root of y, we don't know what that is. It's for any number y, right? So that's what we just leave it as a square root. And note here for number 3, in order to get rid of a cube, the way we get rid of it the same way you get rid of a square, right? But instead of a square root, you just use a cube root. And just as a little note here, again, when you do your square roots, put the little 3 in this little cubby right here. Do you see the little V looking thing, the check mark or whatever you want to call them? Yeah, put the little 3 here. Don't be doing this. This is 3 times the square root of whatever, right? This is cube root. So we want a little 3 in here, right? That's how we write that. And the reason why we do it first in this case is because the 4 is inside the parentheses and then the cube is on the outside. So that's where we have to do that -4 last. All right, moving on. Oh, and some people asked, why don't we put a plus or minus here, right? Because we did that for the square root. Why don't we do that for the cube root? And for the same reason here. So if we take a look at this, this is my example here in one of the periods where I did the same example. So when we go 2 squared, that gives us 4. But when we go -2 squared, that also gives us 4. So there's 2 different answers. But when we do a cube root of the square, x to the 3rd power, x cubed is equal to 8. Well, we got 2 cubed, that equals 8, 2 times 2 times 2, right? But if we go -2 cubed, that equals -8. So that's not the same thing. So we only do have one answer here. So that's why we do not have a plus or minus, because we don't need to. We only get one particular answer for this. We don't get to like how we do with the even numbered ones. Now moving on, we're now going to get to the root of the matter. All right. And if you look at right here, last time we looked at graphically what it's going to, let's see if I can find it. What it means to be an inverse, right? So if we took a look at this, right, we said, oh, we're going to switch the x and the y's, right? We're going to switch them, and then we're going to see what the graph looks like. So remember, we made the x on top, so the positive is on top, and then we flipped it because we wanted the y to be positive over here, right? So this is what it would have opened to the right. And so now we're going to do this algebraically. What does that look like algebraically? Well, here's like the step 0. I'm going to just write down here, like this is step 0. Because the first thing we would need to do if we have a function that looks like f of x, you need to change that f of x to y, because we're going to be doing some things with this variable. So it's much easier to deal with y than f of x, because then some people might confuse that as f times x, which definitely it is not. All right, so here, that's our like step 0. That's what we do at the very first thing we do. If it's not written in function notation, then don't worry about it. You could just start at step 1. But if it is written in function notation, you gotta do this first step. All right, and so once you have that, we're going to, it says first transpose the x and y. And another word we chose to use, and if you notice right there, do you see how they just flip-flop the x and the y? So we're just gonna say switch. Or another person says swap, right? So we're gonna swap x and y. We're going to switch x and y, and that is the only thing we're going to switch. We're not going to switch anything else. So if you think about Freaky Friday, right? Remember the movie? Like the mom and the daughter just switch places, right? They're doing everything else exactly the same, except inside the mom's body is now the daughter's mind. I don't know, but they just switch places. But they look the same, but they switch places. The same kind of idea, right? So we're going to take the x and the y and we just flip those. And once we do that, step 2, solve for x, okay, or solve for y, okay. And then so this is what they came up with, right? So the inverse of f of x is equal to x squared is y equals plus or minus square root of x. Now we're going to do a little bit of practice, and if after this practice you're still like, Miss Lee, I don't even know, what does that even mean? Right, that's okay. We're going to go into this again, okay, the next lesson. So no worries, it's okay. We'll go over it again, just not today. This is not our main focal point. This is just a introduction. All right, so this is our example here. F of x is equal to x squared plus 1. So if you did not already and you didn't look, like cover it up. I wish I could cover it up, but I can't. Pause and then try doing it yourself. That's the best way to learn. Okay, now that you've unpaused and you've done it yourself. So remember the first step, or the step 0, right, is to change the f of x to y. Right, so far so good. So that's what we did. We just changed the f of x to y. And now we're going to switch x and y. So we did that. Look, so it's x equals y squared plus 1. Notice everything else stays the same. Nothing has changed except for just x and y switched places. Will they switch back? Stay tuned for next time. No, they won't switch back. Not in this one. And so we're going to, and now we're just going to solve for y like we normally do. So we're going to subtract 1 on both sides, and then we're going to square root, right? And then we get y is equal to plus or minus square root of x minus 1. There we go. We're not putting in the function. we're not putting it in function notation only because it's technically not a function. So if it's not a function, we can't put it in function notation. That's half of the terminology, like function notation, right? Assumes that it's a function. So if you remember, it's going to look like this, right? Plus, minus, right? So that means that, and remember, it does not pass a vertical line test because it like crosses it twice, many times, right? So therefore, not a function. So we can't write in function notation. Yeah, we can do that. So somebody had asked me, well, instead of switching in the beginning, can't we just solve for x and then switch it later on afterwards? And I was like, well, yes, you can. That is totally up to you. You don't have to switch them first. This usually confuses certain students less. So if you want to switch them first, you can totally do that. But if you want to do it like how we did on our do now, where we just literally just solve for x. So we took the equation, we solve for x, and then if you want to later on switch the x and the y afterwards, you can totally do that as well. So I'm showing you right here. So this is what I can't talk. So we solve for x and then we switched the x and the y afterwards. You can totally do that, and it's still the inverse, right? That order doesn't matter. It's just this book kind of teaches it that way, which is fine. Okay, and here, this one as well. This is what it would look like if we were looking at the inverse. Because normally our x is our independent and our y is dependent, independent, dependent, right? We'd like to keep it that way. So that's why we just leave them we just switch them. All right. Moving on. So now we're going to the square roots. So what we did was we had two different colors, and we're going to graph both the x squared and the plus or minus square root of x on the same graph. And we looked at these points right here. So plot them if you did not do that already. So -3, 9, -3, 9, so on and so forth, right? And remember, in order to plot these points, right, all we need to do is just switch them. Because remember, on the graph, what did we do? We switched the x and the y's. And for the algebraic way, what did we do? We switched the x and the y's, right? So on a table, what are we going to do to find the inverse? You switch the x and the y's. Do you see the pattern here? All right, so yeah, it's the common theme all the way through. That's so hard to say. All right, so this is going to be this right over here. So this would be, x would be 9. So this would be my x, and this would be my y, if I'm talking about inverse, right? So 9, -3. So 9, -3. That's why we have that point right there. And what 2 points do we have in common? And we noticed that it was 0, 0, and 1, 1. And we technically didn't go over this last class, right? But instead of, so remember in class, what we did was we rotated it, going back to geometry, right? And then we reflected it, right? If we rotate and reflect, remember rotating across about the origin, and then we reflect across the y-axis. What we actually did there, we could just do it in one step. Okay, so we could have, let me see if I could draw this line here pretty okay. We could have just reflected it right here. You see what I'm saying? So instead of, so the line would be like this. So if I rotate it on or reflect it on this line, what do we get, right? Let's see if I can do that. So here's the line. No, so here's the line like this, and we rotate it like that. And what do we get? You see? Isn't that cool? Don't you want to do this on your paper? Try it, right? So we just rotate it and we get exactly what we got before, but we just do it in one step. Is that not cool or what? Right, so that's the shortcut way. So, and if you notice, those 2 points that we just pointed out, the 0, 0, and 1, 1, why are they the same? Because if you notice, it is on the line of reflection, right? And if you're on the line of reflection, your reflection is yourself. Like you are your reflection. Like if you go to the mirror and you put your finger on the mirror, where's that finger, the fingertip? On the mirror, right? On the mirror. Okay, and if it's not, and if you're like, okay, touching, it's on the mirror, and it's like this, you need to run. That's some scary stuff there. That mirror is not okay. All right. So here we go. And we were looking for domains and ranges. And if you don't remember, what were those again? Okay, so the domain, remember, is talking about the x. What are all the values that x can be? And the range is what are all the values that y can be, right? And so if you look at this, this is the blue part right here. So the parabola, the one that looks like a U. So if you look, do you see how it's like tilted to the left a little bit? Which means it's going to keep on going left forever and ever, which means it's all going to go all the way from negative infinity all the way to where? To positive infinity. Because remember, where does negative infinity live? Over here, like way the heck over there, like way over there. And where does positive infinity live on the x-axis? All the way over here, like just keep on going. You just keep on going, right? And it's just there. Okay, you can't actually get there. It's like going somewhere where you're never going to get to. So sad. Okay, but yes, so that's why we're saying from negative infinity to positive infinity. In other words, I can put whatever I want for x. So if I put in like inside of this x, I put in like negative 1 million, right? I just go negative 1 million squared and it'll still pop out an answer, right? It'll be some big positive number, but it'll be an answer. If I put in 4,267, right? I square it. Am I going to get a number? Yeah, it's going to be a big number, but it's still a number. If I put some fraction in there, like one, what's a fraction? Let's see, 3/4 or 126 over 257. Can I do that? Can I square it and will I still get an answer? I'm like, yeah. So yeah, so x could be any number. So that's when we say x could be any number, we are saying that it's from negative infinity to positive infinity. Okay, I should say any real number. We're not talking about imaginaries here. Okay, this is the real number line, not the imaginary one. Okay, and then for the y, how low can it go and how high does it go? And notice it goes all the way down to our minimum number, right, is 0, and it goes all the way up to infinity and beyond, right? Actually, technically, you can't get beyond infinity, but that is either here or there. So here's where positive infinity is. Here's where negative infinity is. Like, so this is going to be, so it goes from 0 all the way to positive infinity. Now, the reason why I have this square bracket here is because the question is, can it equal 0? And I'm like, yeah, it can equal 0. So if we're saying that, yes, we're including 0 in our answer. Like, and the range, y can be 0, then it has to be this square bracket. If it cannot be 0, like if there's an open circle in there, or if there's like a thing called asymptotes we'll get into, just not right now, like it can get close to 0, but it can't be 0, then that would be parentheses. And if you notice for all the infinity ones, those are all parentheses, because technically, can you get to infinity? If you can get to infinity, then you haven't reached it yet, because you can always go, oh, plus one more, right? See how it gets very philosophical? So technically, you can't get to infinity. And so that's why we have that as parentheses instead of the square brackets. So do you see the difference? Parentheses, square brackets. Okay. And we notice that the x and y intercepts are both, again, at 0, right? Because that's where they both intersect the x and y axis. And people notice that, well, the domain and the range are exactly the same, but flipped, right? Which makes sense, because what did we do with the x and y when we graphed it? We flipped them, right? So the values are flipped. So the domain of the regular function is the range of the inverse of the function. Okay, so that's why we put these arrows together. And same thing with the domain of the inverse is the same thing as a range for the regular function, original function. Okay, and then intercepts, we notice we're all going to be the same. Is it always going to be true? I don't know. We'll find out. To be continued. IDK. Well, I do know, but I don't know. All right. And so, the other question was then, well, how can we restrict this? What can we do to this inverse function so that it becomes inverse graph, so that it becomes a function? Because remember, we said it wasn't a function. So then what can we do to make it into a function? And so somebody had said, okay, well, maybe we could just take out the bottom half. If we take out the bottom half, then there's no overlap, right? So then when we do the vertical line test, it's just this pink line right here. And yep, this pink line right here. And so that is y is equal to x squared. So we're saying we're not going to deal with the negative x squared. We're just going to deal with just the x squared. Square root of x. I'm sorry, not x squared. Square root of x. So we're dealing with just the square root of x, not the negative square root of x. Only the positive ones. Okay. And if we do that, which part of this, what do we call it, parabola, are we looking at here? What corresponds to this pink curve? Which one is it? Is it the left side or is it the right side? And some people looked at it and was like, well, if you look at it, remember we have that that line of reflection, right? That we can just do that one trick thing, right? If we look at that, which one will be the reflection, right? So let's take a look at this. So we want just this part right here, right? So I'm going to go like this. This part right here, what corresponds to that part? Up. Right-hand side. Did you see me moving? I didn't move, right? Oop, I should go like this. Right-hand side. It's the thing, it's proof right there. Good thing I kept that paper. Think about throwing it away. Phew. So yes, it is this part right here. We're just going to be looking at this right-hand side part. That's all we're looking for. So we don't actually want anything on the left. We don't want, so when x is equal to like anything less than 0, we don't want any of that, right? So this is where we go into our restrictions. So we're going to have some restrictions, guys. So the inverse of this parabola, okay, so of this power function right here, the x squared, is the square root function. So the way we would write that is the inverse of f of x is equal to square root of x for x is greater than or equal to 0. Now this greater than or equal to 0 part, that's what we call the restriction. Okay, why would we call it a restriction? Because that's what we're restricting. We're saying x, you can't be everything. You're only going to be able to be from 0 to positive. Like we're not doing the rest of that, right? From 0 to positive, that's all we're doing. Okay, so I would just make sure that so yeah, that's what it's called. So if you've ever been on restriction, I have not, but if you, because there were things for that. If you were in class, I told you, but we won't get into that here. So so come to class. Restrictions is like, because when you're on restriction, what happens? You don't get to do whatever you want, right? There are only certain things that you can do and a whole bunch of things that you cannot do, right? You're being restricted, right? Same thing, right? So this one, we're restricting the domain. Remember our learning target from today? Like they're all connected, right? So that's what we're going to be talking about. And here, if we're on page 23 right here. We're just looking at that section right there. So when we restrict the domain, what does it actually look like then? This, the green, is actually the radical function graph. Okay, so this is the square root of x. This is what the square root of x looks like. Do you see how it's related to the parabola? It's the same, but reflected on that diagonal line, right? And so this was the original function with the restriction, right? We don't want that left-hand side, we want just the right-hand side. So this is f of x is equal to x squared, as long as for x greater than or equal to, I was going to say x is greater than or equal to x is greater than or equal to 0. That's what I mean to say. So as long, and yeah, this is going to be, and honestly, x, we don't want it to equal anything less than 0, because then we go into negatives. And if a square root is negative, we know where that takes us, right? That takes us to imaginary land, and we don't want to go there. Okay, we've been there before. Actually, it's kind of fun, but we don't want to be there now. Okay, now is not the time. We got to be real, guys. All right. And so if we look at the domain and the range, right? So the domain and range of the green one is of the radical function is smallest on the left is 0, right? For you is this way. And then we're going to go to the right, right? So then we're going to go, phew, and how far right does it go? Like forever and a day, right? So to infinity. So it goes from 0 to infinity. Well, same thing with the range. How low does it go? It goes to 0 right here. And how high does it go? Has an arrow that kind of points up. So yeah, it goes on to infinity. All right. So that's why they both actually look exactly the same. So then what would be the domain and range of the original, right? So the x squared, right? And somebody said, well, don't we just flip the range and the domain so we kind of technically don't have to think about it? I'm like, yeah, you can, or just do it because it's not terribly hard. So yeah, these are the same, right? So whatever we have for the range here, domain there. And whatever we have the domain here for the inverse, it's for our range, okay? Again, x and y-intercepts, still the same. Is it ever gonna change? Let's find out, but not today. And somebody asked me about number 6 about the asymptote. We didn't get there yet. We will talk about asymptotes, but basically what an asymptote is the best way I can think about it right now with something that you've learned already is exponentials. And so this is my attempt at an exponential. And we're living in an exponential time right now, like COVID, exponential. Remember, they're like, we want to flatten the curve, right? This is the thing that they want to flatten, right? The exponential growth, right? Because you start out really small and tiny, and then all of a sudden, boom, it's like done, right? So if I were to say, oh, the whole population has COVID, let's just pretend, right? Okay, I don't want to pretend, but okay, but for this scenario, right? Then I will ask you, when did it have, and let's say it's like doubling every day. Okay, let's say it's doubling. And usually viruses don't double, they usually like triple or maybe quadruple, right? So if they double every day, when was only half the population have COVID? When did that happen? And some people would say like, oh, a month ago or 2 months. It was yesterday. So if today it was all full, right? All, not awful, although it is awful, but all full, right? If the whole thing is full and it doubles, right? So then when was it half of this? Yesterday, right? It was 1 day ago. So it was half full yesterday, and now today it's the whole, everybody, COVID. So be careful, guys. Be safe. All right, that's how exponentials work. So all to say, the reason why I got into this is, what is an asymptote? So if you remember right here, remember if we keep on having the number that we have, right? Having it, so not having it, but 1/2 every time. So we're multiplying by half every single time. We're like going back in time. How many times do we multiply by 1/2 to get 0? You can't. You can get really close to 0, but you'll never get to 0, right? So technically, so this is what we're hoping for, right? We're hoping for a decline, right? So if we start off with like 20, and then we go halfway there, so this is about here, so there's 10, and halfway there, that's about like 5. I'm just estimating at this point. And then it's like 2.5, right? That's how high they are, right? And half of 2.5 is 1.25. When we just keep on multiplying this by half, when do we get to 0? We don't ever get to 0. Mathematically, we never get to 0. But in reality, at some point we will get to 0, because you can't have like half a person, right? So either that person is healed or he's not, or like even a half of a half. Like we're not going to have a quarter of a person. I'm only a quarter sick. Like we don't do that. So at some point we have like this minimum number, right? But in theory, mathematically, we will never get to 0, right? So this is, I believe, Zeno's paradox, right? So if we keep on going half the distance of where you were, will you ever get there? And theoretically, you'll never get there, because you can always go the half the distance, right? But in reality, do we know that we get there? We do, and that's why it's called a paradox. So here the asymptote is, but I digress. The asymptote here is 0. So where y is equal to 0 is the asymptote, because if I can spell asymptote, because that is the line where the graph approaches but never actually gets to. It gets really close to it, but it'll never get there. So sad. Hopefully your journey is not like that. Hopefully you get to where you want to go to, right? Hopefully it's not an asymptote. So there we go. But we'll talk more about asymptotes later on, because we can not only have horizontal asymptotes, we can also have vertical ones and diagonal ones. I'm just saying. But yes, there we go. And we've already made a conjecture about the domain and the range of a quadratic function as inverse. We've, switch it. I can't switch both of them, then it's the same thing. But yeah, so there's the end of that. And we'll continue on with day 2 the next time. Bye.